My name is John Bendella. I work for TransUnion Risk and Alternative Data Solutions down in Boca Raton. And I'm going to be talking about CppComponents, a modern portable C++ component system. Just a little bit about my background. I started with C++ when I was in 8th grade. I convinced my parents to buy me Visual C++ 1.0 and then looked at the manual and said, what in the world is COUT? Then in 96, I was like, what in the world is iterator? And so I got more and more into it. I went to undergrad at University of Florida. There I got involved with Boost and ended up doing Boost Tokenizer. And after that, I went to medical school. And there, after that, I did actually neurosurgery for a little bit. So that's me right there, and we're doing awake open craniotomy, which is doing brain surgery on people while you're awake. After 6 years of doing that, I decided to go into something that had a little less scary, undefined behavior. So here I am. All right, so I gave a talk for a lower level portion of this, and I gave the whole talk, and then one of the questions at the end was, why does anybody need this? So I wanted to just a little bit address that up front. Why do we want or need a C++ component system? Well, header-only libraries are popular. If you remember from the library in a week, that when they were talking about the design goals or not goals, one of the things was a question about whether it'd be a header-only library. And in the Boost documentation, there's a thing saying, hey, we have a bunch of header-only libraries, you don't have to build them. And so why is that? Well, build systems. I mean, I'm sure you can think of a lot more. There's CMake, Boost Build, SCons, Generate Your Project, AutoTools Make, MS Make, MS Build, QMake, QBS. And I'm sure that you can think of some open source project or some other project that you would like to use or have used that had a different build system than the rest of your thing, and so you spend a lot of time trying to get it to work together. Another reason why is in the, I think the Going Native talk back in 2012, Herb Sutter talked about his portable C++ library project. Here's his slide. Was a large set of useful and current libraries available on all major platforms, shipped with and supported by C++ implementations, and composable using consistent types. Basically, you wanted de facto availability as part of all major compiler products. As a way around this, building everything and not having everything, and why did the other languages have just much bigger C++ standard libraries? The reality, regex has been the standard for how long, and now it's shipping with, I think, GCC 4.9. And there's other parts of the standard library. The fact is, different, the compiler vendors, the standard library vendors, they're going to have different priorities than you, and just depending on them to throw a huge amount of stuff that they may find even peripheral into the standard library and expecting them to build it, support it, and ship it, may not be all that practical. What else? Why else for C++ components? Well, package managers. Many languages, Python, Node.js, Ruby, Perl, they've all got their package managers. They greatly simplify, discovering a library, installing a library, using a library. However, with C++, most of these you'll notice they're interpreted. C++ has a problem with, you got to provide a precompiled binary. And the way with the ABI now, you've got to basically precompile a binary for every platform, compiler, standard library, and maybe even debug and release build. If you want something instructive, this is especially an issue on Windows. Go to like the Qt project downloads and look at their downloads and just count how many how many of the builds are for Windows, and each one of them has to be built, tested, and maintained. So basically, if we can provide a stable ABI, we can have a precompiled binary per platform, which is a much more feasible option than having a precompiled binary for every compiler standard library. Yes, question?
Wouldn't it be plausible, at least, to get us off the ground by offering a package management at source level? So we could just say, I need this library, bring whatever it depends on, and I'll build it?
I mean, we could have, the package management at source level, but like I said, the issue is the build systems. Like, what build system are you going to use that? How are you going to test it? When do you update? Like I said, that would be a, start off the ground, but, like I said, it would be, at least part of the way there. Like I said, at least that would be a start, and we don't even have that at this moment. The question was, can we start this, as a partial measure, just of at least having a source level package management, which we currently do not now. Okay, the next part is plugins and extensions. So let's say you write this piece of software. I mean, there's a whole host of things you can write, and where plugins are useful. However, you have a choice. You can either make your plugin interface, just a C ABI interface. You lose a lot of the niceties of the C++, including the automatic memory management, being able to pass, the stuff that you're used to, like string and vector and other stuff across. And you can do that. The advantage of that is you've got, ABI compatibility, ABI stability, and, people from, across, doesn't matter, they can use their compiler of their choice and the standard library of their choice. However, if you decide to do, I want a more C++ component system, well, you've tied yourself to maybe one library, one standard implementation, and they either have it, then if you decide to upgrade libraries, everybody else is going to have an issue. All right, finally, like even if you decide, okay, I'm going to stick with a single compiler and a single standard library, it's still very easy to break ABI compatibility. If you don't believe me, KDE maintains a list of the stuff that you can and cannot do to maintain your ABI compatibility across versions. Along the same line is even if you decide to stick with a given compiler, the next compiler version may or may not have the same ABI compatibility. This is a huge, big thing on Windows where Microsoft makes a point that the given different versions are not ABI compatible with each other. And even in GCC, there's going to be the issue with, with std string. I believe the current standard libc++ is a reference counted implementation, and the standard, basically with C++11 explicitly disallows that. So when they make this change, there's going to be a huge amount of ABI breakage for, everybody that uses std string. All right, so what can we do? How can CppComponents help us? So it's on GitHub, jbandela/CppComponents. It's got a boost license. You can do, commercial, open source, whatever you want. It's header only. I tested it on Windows and on Linux. So Windows is tested with G++ 4.8.2 and MSVC 2013. On Linux, I tested with G++ 4.8.2 and against Clang with libc++. I haven't tested it on a Mac due to not having a Mac, but it should be relatively simple to port. All right, let's look at a demonstration. So last year I tried to put up a bunch of code on PowerPoint slides, which ended up with, I think, probably a lot of people going blind after this after my talk. So give me a second. All right, can everybody see that okay? All right, so what we're going to do is we're going to create a person. And we're going to basically put a person with get name and a set name. And then we'll go from there. And we're passing in std string and returning std string, passing in std string. For now, there's other types we could probably use, but we'll just say string for that one. So this is how we do it. First, we need to define the interface and how the interface goes together. So include CppComponents, include our header file. So we create the interface, which is a struct iPerson, and derive it from a template called CppComponents define interface. And we pass a UUID to it. And CppComponent UUID provides a way to define a compile time, basically define a UUID at compile time, so it has a separate type, but also do it in a canonical form. So basically, you can just do like a UUID gen on Windows or Linux and just put an OX in front of everything and replace the dashes with a comma and just plug it in there. So then we declare our function just like you would regularly. You string get name, set name. You can declare other stuff. There's a whole host of other types you can use if you wanted a vector of strings, if you wanted a tuple of different strings or tuple of strings and ints, you can all use that. And then you use this macro, passing in the person name, the get name, and the set name. So this defines our interface. So we're going to make this portable across compilers. Then what we want to do is, so last year I talked a lot about, during my talk, I talked a lot about all the stuff that go into making an interface portable across different compilers. So now we want to level up from the interface in terms of how we can use it. So we want to create like a runtime class. So if you're familiar with COM or WinRT, some of the terminology may be a little familiar. Like I said, this uses some of the same concepts and terminology, but the implementation is completely different. So I create a runtime class. This is our ID for the runtime class. We'll go over more what this means in a little bit. And then we pass in object interfaces. Say it's got an object interfaces of iPerson, and this is a variadic template. And we call this our person runtime class. And then we type def a use runtime class with type def daf to person. So a runtime class basically takes a bunch of interfaces and turns them into a coherent whole. And use runtime class, we'll talk more about that in a little bit. Any questions at this point? Okay, so next we talk about how we're going to implement that. Okay, so this is our implementation. We include where the interface was defined, and then we just say implement person, CppComponents derived from implement runtime class. It's kind of like the curiously recurring template parameter. Pass back in our implement person, and pass in the person runtime class that we had initially. And then we just put in the names. Just get name, return name, set name, return name. Set name and name equals S. We call this thing to make sure our implement person is registered with this module. And then we put in CppComponents define factory. And any questions on that so far? Yes?
I noticed you're passing the standard string by value instead of by const reference. That must be intentional.
Sure. The question is, I'm passing the standard string by value instead of const reference. Partially intentional, partially to keep the example simple. Basically, the problem is you can't pass by reference because you don't know the internals of each, of how the thing is implemented across the different standard libraries. The way around that is actually with, it supports, I've got a version of string ref, which is pretty close to I think the proposed standard string ref. And for that one, you can, as long as it's a reference, it's past that, so basically, it's a lot cheaper. So we can do that. In this case, we could have done string refs everywhere. I just wanted to, just for demonstration purposes, but like I said, you can replace them with string ref if you want, and then keep everything else the same. So then our payoff comes here. this is how you use it. Include person. This constructs it, and this calls it. And now, even though it looks like that, it has basically reference type semantics. And you can output that. You're not casting the car, and basically, so it's a little bit complicated to define your interfaces and runtime classes, less so to implement them, and even less to use them. Which is kind of where we want to. It's even if the library is a little bit hard to develop, the use should be easy. Any questions? All right, and then this code all built, and I compiled this file with G++ and compiled the DLL with Microsoft Visual Studio, and this outputs this outputs John.
Sorry, man.
Yes.
I guess I'm missing something. The implementation is built with Microsoft, so it's a DLL. Where are you running this?
Sure.
I'm missing the.
I'll show you. Absolutely. 1 second. Pull them down. Okay. So here we go. So this we build the person DLL with CL, which is a Microsoft compiler. This is person CPP, which automatically it'll generate person.dll. And then G++, we build the use person, which generates, I think, an a.exe. So the implementation is built with MSVC, and the actual program where we use it with the main is built with G++. All right, go ahead.
You might want to clarify to people why that's significant.
All right. Yeah, okay, so basically you've got two completely different code bases, two different front ends, two different back ends. The exception handling between the two is completely different. The way the exception handling is completely different. Their C runtime is completely different. Their standard library is completely different. The string in the MSVC is a short string optimization string. The string in G++ is a ref counted string. And basically we're passing them back and forth across each other. And if one of them were to throw an exception, it would actually, kind of translate it onto the other side as well. Yes?
So you would have to publish the exception class using this library.
Well, the exceptions, basically what I'm doing is I'm cheating a little bit. I'm basically doing the same thing that most other people are doing at basically the module level boundaries. And on one side, translating the exceptions to like an error code, 32-bit error code. And, for lack of anything better alternative, I'm actually using basically a 32-bit integer, just like hresult, not really caring about the format, but basically everything less than 0, every negative number is an error. And then I've got a set of so we can map it from an exception on one side, to return an error code, and then map it to the other side and throw an exception again. So that's how that's working. Which is a lot of, like I said, if you were doing this manually, you'd be doing it, by hand or with macros or with a preprocessor or with language extension. Here we're basically just using C++ 11. All right. Let's see. Okay, so now we're going to extend it a little bit. So we are... One second, this seems to... All right. There we go. All right. So here we are now going to extend this. So this is same as before. So we're going to add a constructor to this. You know, because it'd be nice if we could pass in a string. So person. So this is the same as before. Now you've got this thing called a person factory. So it looks like an interface, same as before. And we define two functions, create with name. So actually the name of the function does not matter. All that matters is the signature. We can name this foo and foo1 if we wanted. So we've got a default constructor and one that takes a name as a parameter. All right, so then same thing, person ID. And here's so we have our runtime class again. So we have the object interfaces, which is our person. And then we add something called a factory interface. We can only have one. And it's the person factory for a person RT. And then everything's the same as before. Any questions? So we're basically saying this is our thing. This is our runtime class. We've got these interfaces for the object. And then we've got these constructor interfaces. All right, so this is our, implementation. So you just define a constructor, nothing differently. So this will basically map the implementation of the of that factory interface to the constructor, based on the types of the parameters. And then everything else is the same. And then for our user here, and it prints John and John 2. Any questions about here? Yes.
I'm wondering what happens if you recompile person, but you don't recompile main. What happens?
If you recompile person and I don't recompile
the main program using the use person.
Okay, so I don't recompile this one, correct?
Yep.
Okay, so I'm still using the person here, correct?
Oh, yes. So it's the same code as you had from before. But what you've done is you've gone off and recompiled the DLL.
Okay.
Now it has an extra constructor, but this code, when it was built, did not know it had an extra constructor.
Okay, so basically you've got to keep you have to keep the runtime classes across each other the same. So in this one, you might actually, old person, whatever. So, but basically if you are, so this would actually fail at, it would actually fail, this, if you didn't do that, this would actually fail at compile time because it doesn't know that you've got a constructor.
Okay, and can I clarify by fail?
Yes.
Do you mean segfault, a useful error message, or?
You would get template spew, unfortunately.
Hang on, sorry. How do you mean by template spew? Because if you recompile the DLL, and now you have the DLL sitting there, and you now run the main program, it's just still going to be linked against the DLL, so there's not going to be any template spew.
So basically what this is going to say is, so the person P, so it's got that basically, so let me just see, go ahead.
It means the other way around, that you've got the old main
Okay.
without the constructor, but you recompile the DLL.
Is that what you mean?
That is what I mean.
Okay. So the question is, okay, so I upgrade this and the person who supplies the DLL has not upgraded. No. Yes.
The DLL has the constructor, but the program doesn't know it.
Okay, the DLL has a constructor, the program does not know it. And am I still trying to pass John, or am I just going P? I'm still going P. In that case, there would be a runtime exception saying that it could not create it.
So you are storing a fingerprint of the ABI exported by the component, and then when you come to load it in, it checks to see fingerprint matches.
So what is going on is there is, good question. So let me repeat it. Question is, am I checking ABI matches? There we go. Let me just open up the header file here. All right. So right here, where it says factory interface. So just so you know, this stuff you can put in any order. The order doesn't matter. You just have to specify what they are. But you know, to keep things simple, whenever you don't specify a factory interface, there's an interface that's implicitly specified called default constructor factory interface or something like that. And that interface has a UUID associated with that. So on construction, it will say, give me the factory interface. So the old code, not knowing that it's got the iPerson factory, it'll ask for the CppComponents, default no constructor interface. That interface, this thing will return saying, I don't have that interface. And then that'll throw an exception, something like interface not available or something like that.
Okay.
Yes?
I guess I'm not understanding this mapping that you said when you're defining the constructors, you call them create person or whatever. How are for create name? But you might have other methods that have the same. You said it matched by signature.
You had to have the same signature.
Methods that match by the same. I guess I'm not following.
So basically, for like a constructor, you can't differentiate by name. You can only differentiate by signature. So it's let me see. So it's kind of like the same thing. So the name doesn't really matter. All we have, it doesn't take any parameters. And basically, what this CppComponents construction is doing, we'll get into this moment. It creates it so we can introspect on all the parameter types of the methods of an interface at compile time. So we basically, there's a little bit of meta programming in there to go say, I received this, thing, on the user side, I received these parameters in the constructor. Find me the interface function that matches these parameters and call it for me. And then on the implementation side, there's something that says, for the implementation for this interface, for this method, call the constructor with these parameters. So it's a combination of that. This thing sets up the basically the enough like type info implementation to be able to do that. Any other questions? Yes.
I guess the question that I'd be curious about is, under what circumstances can you recompile either side of the boundary without rebuilding the other and have it still work at runtime? So in this particular case, I see that the old main would have been asking for the old no-args constructor.
Correct.
We've supplied a different no-args constructor, so we've replaced a method on the DLL side.
Right.
I see why that wouldn't work. But
okay.
Are there cases in which you could rebuild just one or the other and it would still work at runtime without having to rebuild both despite
Correct.
additions to the API?
Okay, so the question is, are there situations where we could, stay out of sync with rebuilding them and still have it worked to be able to evolve the ABI? Yes, there is. With the interface, you can define that it inherits from another interface. So we could define another, we could define an iFactory person 2 and add create, with, name and social security number and add it to that thing, right? So when, something that's compiled with it looking at, it'll ask for iPerson factory 2, get that back. However, the original program will still ask for iPerson factory, and since since inherited interface supports its parent, it'll get that one back, and it could use that without recompilation.
Okay, thanks.
All right. All right, so next we will all right, so this is our next step. So this is example 3. We're going to take what we had there, and this time we're going to add a static to it, to person. So we're going to add get population, return an int. Right? So it looks just like everything else. Then we add this thing, static interface person statics. Now this thing, like I said, with this thing, we could add this feature and still be able to be used by the client that didn't know about it. Okay? So this is how we implement it. So this is how we implement it. So implement person, we still have our constructor. And then we just have a static variable count. We increment the count. When we construct, decrement it on destruction, same as always. And we just say static int32t get population. And the same, this will automatically map the implementation of that static interface to a static function in your implement person. And then using it, here, get population. So basically, even like I said, our specification for the interfaces and the runtime class, like I said, it's a little complex. Our implementation is a little bit less so, but our usage is, I assume, with the caveat that this is a reference type, our usage is, what you'd expect from, kind of just using regular C++. We're using, int, we have real return values, not passing in, addresses of stuff to get stuff back. Any questions on that so far? So how does this work? Go ahead, question.
It was just something that strikes me is that it seems to me, am I right in saying this, that for a component that you're exporting, you have to effectively write out twice as much code. So you'll write out the class definition, and then you'll have to effectively duplicate that class definition to say what the component definition is. Would that be an accurate assessment?
The question is, for the, when you create a component, you're duplicating the definition of it. You write the definition in the header file, and then in the implementation file, it's almost the same as the header file. Is that your question?
That would be my question.
Yes, that is correct. And I really don't see a way around that type of thing. Anytime you want to, basically you're wanting to separate the interface of it from the implementation. There's different ways we can go about it. One is, there's IDL, which, tries to do the same thing in, which like, the other, like COM or, so however thing they use, they often use IDL for the interface definition language. And then there's some other, preprocessor compiler that'll generate, some C++ code that you then implement. Or else, if you use something like, C++ CX or, C++ CLR, that metadata is generated by a special purpose compiler. My thing was, let's see if we can generate that metadata in C++. You know, a language you're familiar, we don't need another tool, there's not another tool to maintain, and let the C++ compiler generate that for us. And, you know, I would hold that, you know, doing it this way is probably not that much longer than if you did it manually in something like IDL or something. The only way I think you could get better is with built-in compiler support.
Just thinking of a Clang library that would generate it for you.
Yeah, Clang would be nice, yeah. Right, but like I said, and then, like I said, it's, but like I said, we've got something to output to, and, I bet, Clang could do that, make it, nicer. But, there, any questions? We have. So how does this work? So I gave a talk last year on binary cross-compatible interfaces. It was very, very code heavy, not as much, usage examples, and we went into a lot of detail over some. I will, for some of the details, refer to that talk about how we got there, what the design process was, and some background about calling across interfaces, but I'll summarize that for you. So this builds on and extends last year's talk. We borrow many ideas and terminology from COM and WinRT. The implementation doesn't use any COM or WinRT, uses only C++11 to be portable. There's a little bit asterisk by that. So these are our assumptions, but they're commonly implemented. Number one is that we can specify packing to generate and create identical binary layouts of a trivial structure across two compilers. Most things support the Pragma Pack 1 for trivial type structures, basically because a lot of the platform ABIs rely on them. They will work across the compiler. So this, like I said, works on MS, GCC, Clang, and GCC on Linux. And then we're able to specify platform calling conventions for a static member function. So theoretically, like a extern C function and a static member function can have different calling conventions, but but the compilers that are currently out there support a way to either make them the same or else they make them the same by default. Okay, so these are from last year's talk. So how does this work? So this is the heart of what enables, so basically we're going to talk about the cross-compiler stuff. So when I say the cross-compiler interface, I'm talking about the lower level, bit level thing. When I say CPP component interface, I'm talking about the high level thing that we defined. Is everybody good there? So basically, we have this, basically a function pointer. And portable base is basically has a v pointer. Points to like a table of function pointers. Then we derive from there, and then for our purposes, we add another pointer to some extra data that we use, and we'll go over what we do with that differently. And then we have a thing that based on the size of our v table, how many functions were declared, we generate like an array of that. So data, and then the v table n. And then we have something where you can get the portable base. Any questions so far? All right, so this is the cross-compiler interface. This is what CPP, CPP components construct. This is what it creates for you under the hood. So this is how we define an interface at the low level. So we have a struct, a template, T, and then we inherit from something called define interface. But basically, we had this thing called a cross function, and we give it an ID where the 0th one, the first one, and then we have std function type signature there. And then we had initialized with the this pointer, in the constructor. And what this is doing is because it gets to this pointer, cross function can, and this eventually inherits from either portable base if it's an implementation, or something that holds a portable base there. So based on that, and this T tells us, basically we pass in a different type saying, are we going to use this or are we going to implement it? So on both sides, cross function basically overloads the function call operator, and it basically goes in there and indexes into the portable base, that vtable, casts that pointer, and you're allowed to do that by the C standard, to basically something derived from the type of this, and calls that. When it's on the implementation side, when T tells it's an implementation side, what it's doing, it's basically assigning a function to that will, call out and go to the, to our high-level function. All right, so let's look at some code here. All right. So this is nice and buried. So basically, vtable caller. So this basically the operator function call operator uses this vtable caller to actually do the call. And this is a little bit modified from the code just to simplify things a little bit. So basically, it takes the return type, what the parameters are, and it exports a thing called vtable func. And it basically takes the function pointer, which is the void, which was that void, not taking any parameters function pointer that we had from the vtable, takes a pointer to the portable base, and then takes all the parameters. I mean, it does a little bit something to just avoid from needless copying, but this is good enough for now. So the heart of this is something called, there's a cross conversion, and there's a either cross conversion or cross conversion return. So these are basically template types that are specialized to say, I have this type, give me a trivial type that I can use either for return or I can use to pass in stuff. So basically it sets up, and return is a little bit hard, so it sets up, creates the trivial type for the return, initializes it based on specialization, and then detail call just casts, the return value of the parameters and calls that function. So basically, it casts that original, the pointer fun void to, so this type of function, and calls it, passing in the portable base, and then all the conversion parameters that are converted to their trivial types. And then basically, if the return value is less than 0, it'll map. There's something called map exception from error code, so it'll throw an exception. Otherwise, it will finalize the return and then return the return value. All right. Any questions? Yes, go ahead.
So, how do you support custom parameters?
We do support custom parameters. Basically, it's not in this talk, but I've actually got how to do it. Basically, what you had to do is you have to override that cross conversion for your type that you want, and basically that involves specifying a trivial type that you can use, and then how to get there to there and back again. And then there's a default return thing. I will show you a little bit how that works for like string. Okay. This looks scary, and I don't know how many internal compiler errors I got before I found out the right formulation to make this compile across Visual C++, Clang and GCC. But anyway, so it's not exactly like this, but this is close enough. So we take the parameter n, so that tells us where we are in our vtable. So which vtable function, what the parameters are. And then we take this thing which looks ugly. So basically we take a class C, which is basically a class, and MF, which is a member function pointer type, and then a member function of that thing, and then the return value. The reason we take that, because the compiler knows at compile time what the member function is. It can basically, instead of doing indirect call to that member function, can do it at compile time. Or basically decide what it's going to call compile time. So what we do is we grab our vtable base, vtable n base. We know we're on the implementation side of it, so we can convert from the portable base to the vtable n base. We get the data. Remember, we had the data in the vtable n, and we get that data there. So there's a way that we can store a function pointer to it. Sorry, the class pointer that'll be implementing it. And then we call cross conversion do return, which helps with the return value, and we'll look about that more. And then we convert all these converted types back to the original types, and as well as the return type, and then we return 0. And if that throws an exception, we map it back to an error code and return. Any questions? All right, and so you were talking about how we went from there to. All right, so we're going to talk about, okay, how do we implement a custom type? There's a little bit more, but at the basic level, here's how we do it. So this is how string works. Cross-compiler interface, it's all in something that's surrounded by the pragma pack, pragma pack push 1, I think, and then pragma pack pop. Just to be doubly safe for some things, I think this on the compilers will come out to the attribute packed 1, I think, the extension stuff. So basically, we have this. So basically we're going to do a conversion for basic string. So we type def what we're converting to as our original type def this thing, which is a trivial type, to our converted type. And then to go to our converted type, we just ret.begin is s.data, ret.end is s.data.size return, right? So we're doing it before we call across. And then to go back to original type, we just reconstruct a string, begin and end. Now the problem with that is your returns are going to be, right, you're going to return, if you use this for returning, you're going to be returning to basically dead memory. So you want your returns to be different than your parameter passing because your memory types are different. So basically, we define this cross conversion return, which you can specialize as well if you want to do some stuff. There's some stuff that specializes it as an optimization, but this thing will do it in general. If it's a trivial type, it'll just pass it across as a return thing. If it's not, it will end up creating this structure. So basically what this structure is a function pointer called transfer that will transfer something to a destination from a converted type. And then we store the destination. So this is what this does. This is what the transfer function is. And this transfer function comes from the calling side of it. So basically, we use our p destination, that pointer that we've got, to go back to our calling destination, which in that case might be a string. And then we convert it to our original type. And then if there's an error, we trap an exception and return an error code. So then we override initialize return, which says this is the return type, and this is the converted type. So return type would be string, converted type would be, that structure that we have. And we say the transfer function is a do transfer, the destination is there. Now this thing gets called before we call, so we're still on our side of the ABI. And then the do return, well, the do return says, okay, I've got the converted function, transfer it, so that way you can, so on your, on the DLL, say you're calling, you say, call this function that'll transfer the data back into that return type. So this is how you would go about, you override these two functions, and then you can go, that you specialize that template, and then you can define your own custom types. On the project page for that one, if you look under wiki, it's not off the index pages, but there's a thing that'll walk you through defining a custom type if you want to. Okay, so out of the box, what do we support for parameter and return types? You can pass in unsigned car, wcar, car16, car32. You can pass in int 8, 16, 32, 64, float, double. You can pass in the all pointers, constant pointers, and constant references of the above. You can pass in void and bool. You can pass in basic string, vector, pair, tuple, and then the chrono time points and chrono durations. And then from the C++ string ref, you can pass in the CppComponents string ref. It's basically the same thing as the Boost version. A couple modifications. One was to make sure that it was a trivial class, so it had to do something with some of the default copy constructors. And then I added a modification to be able to tell if a string is null terminated or not. Because with this current string ref, if you have a string ref, you can't tell if there's a null at the end of it. And it doesn't matter as long as you're processing that, but the minute you want to say create a wrapper for like a C library, there's a lot of them that expect you to pass in a null terminated string. So if you don't have that information, you're either struck saying, well, I hope they got it right and pass that in, or else I'm going to be safe and allocate an std stringer with a null terminated and do it. This allows you to be, to be able to tell if, hey, is this null terminated or not? So so if it is null terminated, you can pass that in. Otherwise, you can allocate memory and pass that in that way. It also supports CppComponent use. This is what we use for our interfaces. We can talk more about that. And then CppComponents function. So this is basically an analog of std function. The reason I didn't directly support std function is because to be able to pass them across efficiently, you had to be able to get at the internals of std function. And basically, so if you try to do that, what you do is you'd be adding a wrapping layer on each round trip across. So you'd add your layer, and then, one across, and then coming back, you'd add another layer, so it would just grow there. So, if you want to pass a function type, you can use CppComponents function. Okay, so we'll just look at the stuff. So define interface, we saw that. So what it takes the UUID, and it takes a default base class of interface unknown, which is basically IUnknown. So it provides, it does the stuff with the UUID. So that way, because of the UUID is unique, this will be a unique type, and we can also query for it at runtime. So interface unknown, I call it interface unknown because IUnknown will probably clash with a bunch of other stuff, but it basically provides query interface, add ref, and release. And the implementation is actually binary compatible with COM. So all of your stuff that you're creating are basically COM interfaces at an ABI level, except for the types. So UUID takes, basically we take 8 bits there, 4, and then we use uint64t for the number of bytes, and then basically it allows you to pass it in canonical format. Okay, CppComponents construct. This does a lot of stuff. Basically what it's doing is you declare those, you're declaring your functions for the interface. This is basically taking those based on the type of those functions. It is creating that interface we talked about earlier with the cross functions and filling them out correctly. It's also creating a bunch of kind of like introspection info, basically what the, basically all the type names of the cross functions that it's generating. So, so this information is what's used to allow the mapping between the constructors and the static functions. It also creates a couple of like helper functions to be able to map from the names of the functions down to the type of, down to the implementation type transparently. Use, so it provides the ability to call interface functions and it manages reference counting for you. Runtime class, this assembles the various interfaces into a coherent whole. Use runtime class inherits from each of the object interfaces, and then it maps the static function calls to static interfaces, maps constructor calls to factory interfaces. And then implement runtime class, it provides the interface of the runtime class, it provides the interface on known implementation, it maps the object interfaces all to member functions. Note after the first interface, just in case there's a collision, the first one maps them straight to the function name. After the second one, it'll map them to interface_function. This is just an implementation detail. It is transparent on the user side. Maps the static interfaces to the static functions. And then what it does, it has a static variable of a class that implements the factory and static interfaces. So the factory and static interfaces, their implementation is actually created at, is created as a static variable. And then it registers itself in a factory map saying, hey, if you're looking for a factory with this name on it, that's me. So then we had the macro CppComponents register. So basically all it does is create in an anonymous namespace, creates this variable that'll never be used and a function that'll never be used, basically to force the static variable implement interface to get instantiated. Otherwise it doesn't get instantiated and then the constructor never registers it, so we don't know that it's there. Any question? CppComponents define factory. So this is what it looks like. It's a little bit long. All right, so this defines our exported functions. These are the only three functions that actually get exported from the library. So basically something called getComponents factory that says, hey, pass me a character string, get me back the components factory, get me back something that'll provide the factory and static interfaces. Something that says, hey, am I still in use? Do I have, are there outstanding reference counts? And then the last one is basically to say initialize it, module initialize, and then we'll go over what those are used for in a little bit. Yes?
How thread safe is all of this?
Okay, so the goal is to be thread safe. There are locks around some critical structures. Most of these structures are only happening at initialization time. This gets up, then the rest of it is read-only stuff. So the question was, how thread safe is this? The goal is to be thread safe and be able to use it if it's, modulo bugs in the implementation.
I was wondering, if you had multiple threads all loading multiple components simultaneously from multiple threads, how well does that work?
So basically let's see if I talk about this. So the question is, if there are multiple threads attempting to load multiple components, at the same time, how does that work? And basically, in the executable itself, so the executable, it maintains basically, it's a cache of all the modules that have been opened. And access to that one is serialized. So basically, it's like if it's not in there, it will add it to it and, and then serve it out of that one. And then you saw that function where it says initialize and it was passed some pointers. So every module actually gets passed a interface pointer back to that, the master one. So it's synchronized across all the different like DLLs or SO files. So even if different ones are calling them, they're all going to the same local place. So that way everything is in sync. So how does this? So how does constructing a runtime factory use runtime class work? So we asked for an activation factory for a runtime class ID. That was the person, bang person. And then we query interface for our factory interface. So this was where you were asking about if they were compiled out of sync, how it would fail at runtime with an exception. And then this is actually the syntax that you use for query interface. So that you're not passing in UUID by hand or anything like that. You just pass in what factory interface you want, and it returns that. And then based on what types were passed in, we call the appropriate interface function. How do we get the activation factory? Well, we look up the module that implements that class runtime class ID. We load and initialize that module if necessary. Otherwise, we cache it. Ask the module to provide us the activation factory if it implements it. And that module, there's a local factory map for all the stuff. Remember, we had the register implementation, so in which the constructors of the factory static implementation registers themselves, and it returns that. So basically, we have this thing called iString factory creator, which may not be the greatest name. But anyway, this is the one that's kind of like the master list of managing what modules get loaded and unloaded. So it has several of these functions. One is the add mapping. So you can map from a class name to a module name if you want to. Get class factory given a class name. It'll try to get the class factory. It'll get the class factory if you want to give it a module name and a class name. There's something called free unused modules. It'll look through those, ask them, hey, do you have any ref counts outstanding, and free those. And this actually, so there's only one copy of this across the entire, across all the DLLs plus the executable. So basically, the runtime class IDs are of the form module class name. So you have person, person. So by default, if we don't do anything, we'll load the module either .dll or .so file and ask the module for the activation factory for that. If the module is absent, we'll look if there's a prefix mapping. So a prefix map also, so the add mapping method from before, that allows us to override it. So instead of naming it person, I just called it person. And then I had to add a mapping because it doesn't know what module that is. Say, hey, map everything that starts with, say, PER to person.dll, and it would do that. This is useful, say, if you're implementing stuff, kind of like backwards, mycompany.division.thing. You can map a bunch of class names into a few modules. If it's of the form bang class name, it'll only look in the local factory map. So you can use something if you want to create something that you want to use locally just in that module, don't want the rest of it to see it, kind of like a private thing, you can do that. So how modules are loaded, we use load library on Windows or DL open on Linux. We call the exported function components module initialize, passing an iString factory creator. And then that one, then the module itself tells whenever I need to look up something, I use this thing. And this makes us sure that the changes that we change across from the class IDs to the module mapping remains consistent across our whole instantiation. So we can use this to get like a very simple form of dependency injection. Any questions so far? All right, beyond the basics. So we're going to look at simple dependency injection. Okay, so let's say, we're using something, so our modules may want to print something, right? So we can't have every, but the main exe is the only one that knows exactly how it wants to output something, because you have a different standard library implementation, so everybody can't just go calling cout. The actual executable may be a GUI program that it wants to redirect somewhere. So how do we make sure that everybody's consistent? So let's say we create like something called ioutput, and we have something called print string s. And we have a thing just called output, and we create the runtime RT and the output. Same as before with the person. Any questions? And then we have our person.h. Same as before, but we added a method. In reality, we changed the UUID or add it as a different interface or something, and say hello. And this will output that. And then here's our implementation. Say hello. So we include output.h and go output print string hello plus name. And so when we do this, this will actually use the implementation that was provided in the use person, and use that to output it. So basically, we implement output, and then we say this is our output for print string. So if instead of using a console app, say I'm using I'm writing a GUI app. Instead of this one, I just say output to a edit box, output to a static library. Or if I'm writing a web thing, output is part of the web page. And and my changes will work across all the modules that rely on this. Any questions so far? All right. We'll skip over this generally. There's because of the way we can have either overloads or templated functions, there's a way to be able to add them in there. We can talk about it a little bit later. You can come talk to me afterward. Basically, there's something called TPP called interface extras, static interface extras, and then we can actually even have templated constructors in there that will map to the map to like the underlying type. And then we can have parameterized interfaces. And the trick with that thing is we need our UUIDs to be unique. And the way we do that, we actually use the version 5 UUIDs, and there's, in Boost UUID, there's actually an SHA1 name generator. And so we abstract that with something called combine UUIDs, that we can combine the UUIDs based on template parameters so that we can generate a version 5 UUID, and so that we can guarantee that each interface is actually unique, even across its template instantiations. All right. Sometimes, say for working with plugins, we want to load a module explicitly. You just have a list of names of stuff, and you want to load it explicitly. You can also do that as well. So let's say, our person stuff is the same, and I'm going to create these two things, one called, Bandela.personH. We use the same thing, implementation. So every time you assign a name, I put Bandela behind it. And then I have a Smith one, and this does the same thing every time it does a Smith name behind it. So then in my use person has something called dynamic creator. that if you pass in a module name and a person ID, it'll use that one to actually create it. And the open parentheses close for just calls the, just the default constructor. And then if I output these, for this one I'll get John Bandela, for this one I'll get John Smith. So like I said, makes plugin creation or extension, fairly easy. And then finally, we have call by name, whereas sometimes we're wanting to, if we're interacting with scripting languages or other things, we can basically, we want to be able to, instead of calling it by the vtable, call by name. So let's say we've got this thing called math, and we have add, we add stuff, and then we have this interface math that has add, and then we define an interface called dynamic, but basically it's called a call by name interface. And there's in CppComponents, there's a function called make a call by name interface for any other given type of interface. It can make something that'll call by name. And then you can use that to basically do stuff dynamically. So this is just a little function that says, hey, tell me what modules you want to load, loads the module, say, hey, enter a function name, and based on that, it'll call a function name, passing in the parameters. All right, any questions up to this point? So this is just all the stuff with CppComponents proper. Yes?
So how do you keep the runtime, the C runtime, from colliding with each other?
Well, both of them are loaded with with the visibility hidden. On Windows, I'm basically statically compiling it, and the memory management is all managed, by the module itself. So we never call newer delete. It'll create something for us. When it's done, it'll destroy something for us. So it'll keep them that way separately. And at least on Windows, like I said, the underlying principle works, for mainly with like COM modules are themselves allowed to use different runtimes, to keep ABI stability. So that's how we're using it. That's how it works. All right. And then just one more thing. So, all this stuff is good for, just your synchronous stuff. But, what about, nowadays that everybody is going to, multi-threading, asynchronous stuff. So, just some of the stuff we were working on to do that. So basically so I implemented a type of channels, some of the executors from the executors proposal, but making them interfaces, modifying them in that way. And then an await based on boost coroutine. So basically you can have a function, let's say you've got a printer, and it receives a channel of int32s, and basically it says await is future. Whenever the channel tries to read, whenever it becomes available, I test if there's an error code. If it is, I return. Otherwise, I output whatever that value is. And then I've got a generator. So let's just say I'm going from 0 to I equals 0, I is less than 10, I++, and then call await on the channel.write. So the channel.write it returns a future, and the future actually won't be completed until somebody reads from it. So that way this keeps them both in sync. And then at the end it calls channel.complete, saying, hey, there's no more writes going to happen to this channel. So we've got a loop executor, we create it, we make our channel. COA sync is kind of in the same thing as the new async proposal that takes a executor, but this thing actually makes it a coroutine, so you can use the await on it. And then there's also when all implementation for when all both of these are done, it calls make loop exit, which is an analog, of what is in the proposal there. Calls loop on it, and then it calls f1.get at the end to see if they threw any exceptions and to rethrow them. This thing will actually go through and on a single loop, on a single thread, will print out 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, where do we want to go in the future with it? So what am I working currently? So an ASIO-based implementation of executors and async network I/O and timers based on that. So basically you can build it once and be able to use it across various implementations. Boost coroutine-based await implementation. Working on maybe using a nice wrapper for libcurls that, easy to, just say, hey, I want to download a web page, scrape it asynchronously, be able to do that for you. And then maybe starting work on a C++, on a package manager. Use this kind of technology to create a package manager. Future plans, port to Mac, maybe do remote components over the network, kind of the same stuff where the constructor was mapping to, to constructors and interface functions, map those to network calls on either side of the interfaces. Maybe a QML JavaScript interface using that call by name stuff, so you could, easily just create a component and be able to call into it. Possibly if there's demand for it, a COM or a WinRT wrappers to be able to use this type of thing to actually create, the platform-specific stuff, and an HTTP server library. So the code is at CPP at this address. Try it out, give me a feedback, tell me what you think. If there's an existing library that you like, that you're always getting tired of recompiling and rebuilding whenever you try to upgrade compilers or do anything, write a C++ component module. If you have any questions or anything, I'm happy to help you with that. Feel free to contact me. And let's try this out and see if we can build like a larger ecosystem for readily used C++ components. I'll be happy to take any questions. Any questions? Yes.
Yeah, I first want to say thank you very much for presenting this. It's something which is we continually ignore in C++, and we keep adding lots of fancy new compile features. We ignore API management. I think it's become an impediment to the future longevity of C++. And as you know, John, I've done my own component implementation.
Right.
Very different from yours, actually. I hadn't quite realized just how difficult it is. I would say that for wider adoption of this, I do think we need something to help with the generation of the interface files. If you remember back when COM first came out, you had to write out pretty much the IDL by hand. And then someone quickly realized, well, we can build in a tool that doesn't spec the code. And
right.
Create some IDL for us. That eventually evolved into .NET. And, quite successful in what it was. And I'm still thinking here that I'm not necessarily saying that the tool set should automatically generate the interface files straight off, because a lot of the time you don't want that, because that would mean that the interface would change as quickly as you change the source code.
Right.
Bad. But what you do want is, if I come along and I add some method, foo to some particular class, I probably would quite like it if the tool set went off and generated a new initial default implementation wrapper for that. It shouldn't really go off and modify ones that I modify. So if I modify a parameter, I want that to be echoed into the interface by default.
Right.
But it would be handy if that happened, and certainly it seems to me that libclang would be a very quick and easy way of getting the appropriate interface files to be generated out. So that's my first observation, and I was hoping maybe with your roadmap you might want to perhaps think of that. The second thing I was going to suggest is that the COM integration, specifically the WinRT integration, I think that is an underestimated value add. As much as certainly a lot of people at the conference here, especially because of the ongoing problems with Visual Studio, we tend to focus a lot on Unix and POSIX and OS X, and Windows isn't as prioritized as perhaps should be given its position in the marketplace. And if we had a I mean, Microsoft have their own set of extensions to integrate C++ with WinRT, and there's nothing wrong with that. It's great, but none of it's portable. Whereas this at least offers the chance that you can write one set of code with one set of componentization, and you'll have a component system that runs on Linux, on OS X, and on Windows. And admittedly, fair enough, it might be a WinRT model throughout, but that's actually probably not terrible in the bigger picture of things. And I was just hoping, basically, you might consider perhaps bumping up the WinRT COM integration. Because certainly one of the things I noticed was that you require the types to be passed in and out by parameter. They're a very limited set. And because of that, I can certainly see that in my future use of what I'm intending to use your library for, that the fact that you are limited to, effectively you're repacking each of the STL types that goes through every single time. I can see that as being a performance issue is the first thing. I can see it also that people are going to complain that when you have everything compiled by Visual Studio from top to bottom, and you're still repacking the parameters every time they go through an interface boundary. I can see that as being an issue, and I can see that the fact that you can't just pass in any old arbitrary type, which is on both sides, as being another issue. You have to wrap them all up with conversion types. And again, this is something where an automated tool could do a lot of the heavy lifting for you, and then afterwards you tweak it as appropriate. So those are all my observations, and it is a great talk, and this is the stuff that we need to really think about for C++ 17 in a big way.
All right, thank you for this. Let me just repeat it for the camera. Let me just let me just summarize.
We heard it.
Okay, you heard it fine. Okay, so yeah, thank you very much. Yeah, especially like I said, I think in terms of generating the initial interface, you write an implementation file or something that says, hey, I've got this code here. This is a class I have here that I use. Make it a CppComponents. Make it compatible with it, and it'll generate the interfaces for it, and that you can use it. So with COM and WinRT, that's something I've been thinking about. Basically, my call by name is almost iDispatch, just with a different name. And also that, where that runtime class ID, now it's a constant char, whereas basically all it is changing to HString to use it with WinRT. I mean, there's a little bit of stuff. So some of the stuff I built in are actually templates, and you can parameterize that. And I actually had a little while ago a WinRT version of this that actually let you use Microsoft WinRT components from GCC. And to address the other issue about, we're packing and repacking types across. I agree that's an issue. A solution to that would basically, you'd have to create types, an ABI stable type, that say, okay, this is the type that we're going to use. And that one you could pass around everywhere, whether you make it via an interface like the CppComponents function, or however you're doing, you could have your own string type that's specific to this one. That is a possibility. One is we're going to have to get everybody to agree on it, and two is I didn't want to introduce another string type because everybody's going to say, oh, I had to throw out my old, my code that works. I want to be able to use C++, not some crazy thing that you have addition. Where if this becomes bigger, greater, more adopted, and there's a demand for it, the performance things, that would be something that would be fairly simple to add. I thank you for your question. Any other questions or comments? All right, then I guess we'll finish 5 minutes early. Thank you very much for your attention, and have a great rest of the day.